What you doing in there? Oh, okay. This is lesson 64, identifying, writing, and graphing inverse variation. Let's talk about what you're going to need today. Got a pencil here somewhere. Need a pencil. Need your notebook for writing stuff down in, because you want to be able to use this on the test. I'm going to give some really good stuff today that you're going to want to use. You probably need some of this type of graph paper that I gave you in the email. Print off a copy of that to use today. Homework sheet, that would be useful. You probably need a fake mustache, come in handy, and a small plastic model of the human stomach. One of those as well. Oh, graphing calculator. We're going to be graphing some stuff today, so you're going to want to have that out, and I'll give you the instructions on which buttons to push. Okay, let's start off first with that you've had, I believe you've had direct relationships, so direct variation, where if one thing goes up, so does the other one. Like age and shoe size, pretty much normally, one goes up, so does the other. Yeah, okay. So let's define inverse variation. A relationship between two variables, and most of our problems today our two variables are going to be x and y, so we can graph them, whose product is a constant. That means that over here, I'll give you an example. Here's my two variables, x and y, and the product, or the answer when I multiply the two of them together, is just a constant. It's just a number, 12. And so let's do a little game with that. We'll take this and we'll say, if this thing right here is true, x times y is 12, and x is 1, y must be 12, because 1 times 12 equals 12. If x is 2, y must be 6, because 2 times 6 equals 12. If 3 is x, y must be 4, because 3 times 4 is 12. If x is 4, y must be 3. 4 times 3 equals 12. And if x is 6, then y must be 2, because 6 times 2 equals 12. As the numbers in the x list increased, 1, 2, 3, 4, 5, 6, the numbers in the y list decrease. 12, 6, 4, 3, 2. Now, as these ones go up by 1, and 1, 2, 3, 4, these ones do not go down by 1. They go down by 6, 2, and 1. So it's very different than just a direct relationship where one's going up and the other one's going up in the same exact kind of way. One's going up and one's going down, but at different rates. We can write this in a couple of ways. We're either going to say that x times y equals k, and k stands for our constant of proportionality. It might be 12, it might be 2, it might be -1, it doesn't matter. Whatever that number is, constant of proportionality. Or we could write this kind of like we would graph it. Y equals k over x. This is the one that you oftentimes look for. This is kind of that first definition of a product, x times y equals a constant. But this one right here is usually the way that you will visually see the problem and identify by its shape that you're working with inverse variation. So I'm going to give you kind of like a data chart here that you'll copy down. You can hit pause on the video and copy what you see on the screen. And that'll give us, that'll take the longest amount of time for what we're doing today, and then we'll go through some examples and show you what it is that specifically that you're supposed to be looking for. Okay, I'll give you the left side of the chart first. We're going to compare direct variation to inverse variation, what we're doing today. If you've got direct variation, get out my pointer here, you're going to have either a format like this, where you might graph it, y equals a constant times x, or you can see the relationship between x and y together, that y divided by x is a constant. That is the ratio of y to x is a constant. And so what happens with direct variation is that if the value for x is increasing, then the value for y increases as well. And if the value for x is decreasing, then y decreases as well. Graphically, this is what it's going to look like. As x increases, y increases. So our graph will look, it'll be a straight line. And in this case, if k is a positive number, then our graph goes up. Okay, very simple. Like visually, you see a straight line going up. You want to think direct variation. An example of a graph like this would be y equals 2x. Very simple graph that you can do on your graphing calculator. And the key word here is ratio, because in this format here, it's the relationship in a ratio of y to x. That is the thing that stays constant. So you can see that if the ratio is 5 to 2, and the 5 increases to 10, the 2 has to double as well to 4. 10 to 4 is the same thing as 5 to 2. That stays constant. The value of that ratio stays constant. And the other side magically appears. So let's compare the two now. If we put it in a form to graph, we'll have y equals constant over x. Or if we want to show it as the relationship, we have the product, y times x equals that constant. So this is what we saw when we made that t-chart. If x was increasing, then the values for y were decreasing. It went 12, 6, 4, 3, 2, 1, as x was going 1, 2, 3, 4, 6. If the values for x were decreasing, the values for y would increase. So if I take those numbers that we use, the 1s and the 12s, and we graph them, just connect the dots here. There's the first one, second one, third, fourth, fifth. Then it makes this curve shape. That's what you want to look for when you're looking for inverse variation. You're going to see a curve like this. In fact, if you take your graphing calculator and you graph y equals 1 over x, you're going to see that shape, at least over here in this quadrant. Let's go ahead and do that. I'll switch over to the other camera, and we'll look at the graph of 3 inverse variating graphs. Okay, you got out your graphing calculator, and you can go ahead and push that y equals button to get these. And all I'm going to do is I'm going to go 1 divided by x, 2 divided by x. Where's x? There we go. Oops, divided by. And 3 divided by x. And we'll get the exact same shape. We've got blue, pink, and black here. 1 divided by x, 2 divided by x, and 3 divided by x. So you can see a similar shape. There's that curved shape rather than a straight shape. And it's high when it's close to 0, and it gets low as x increases. We're also going to talk about what's going on in the middle there in a minute. I just wanted to show you the graph of those. Okay, we'll look at some of their examples here. And basically, in the examples, all they want you to do is to say, is this inverse relationship or is it not? Okay, and probably one of the quick key things that you want to do is to make sure that your y is on one side and everything else is on the other. Well, I guess either of the ways that I presented it in that chart you can look for. So this first one right here, y is to 6. Well, this is the constant, so it needs to be over here by the x. So if you multiply both sides by 6, move it over to this side, we can rewrite this as y equals 6 times x. Okay, so k is 6. This is y equals k times x. That is direct variation. This graph would make a straight line. This one right here, you notice that it's a product, x times y, and we already know that was our key word for inverse variation that we were looking for today. If we change this to y equals and put it in like a graphable form, you'll get 5 divided by x. Divide both sides by x, y equals 5 over x. And that will give you a graph that looks like that. Inverse variation, obviously, But again, just notice the form that it comes in and compare that to that chart, and you'll have the exact thing. Now, because we have this thing about it being a product, there are a lot of things in the real world. I'll give you one example in chemistry, in the gas laws, where you do have products being a constant. Okay, I'll give you one example. In the book, they mention this, what do they call it? A product rule for inverse variations. And they say, let's look at a before and an after kind of event. And the P stands for pressure and the V stands for volume. And so I brought with me here a plunger thing. Do not ask me where I got this from. It probably grossed you out. This is a rural area. We have a certain amount of air that fits inside of this, and I'm gonna close up the end here. And so we have a certain amount of volume in cc's, and then I got the plunger, and I'm gonna increase the pressure on the plunger, and look what happens to the volume. Okay, the pressure is going up, the volume is getting smaller until can't hold it anymore because the pressure was too high. So as the pressure went up, let's say that the pressure was 2 and I increased the pressure to 4. The volume, let's say that the pressure started off as 1, it got smaller. I decreased it by quite a bit. And here's the question then, what would be the volume at the end if these things must be equal to each other? 2 times 1 is 2. 4 times volume 2 must be equal to that. So if we divide both sides by 4, we find out volume 2 must be half of what it was before. That's what it has to be if I doubled the pressure from 2 to 4. The volume would get smaller. So that makes sense. If the pressure goes up, the volume must go down. They have an inverse relationship to each other. In these product types of situations where they want you to evaluate product rule and see how it plays out, and like the pressure and volume problem from chemistry, they're always going to give you 3 of the values and you have to find the 4th one. And that's fine. It's 3 knowns and 1 unknown, and that's enough information for you to solve any of these. In the last example I gave you pressure 1, volume 1, and pressure 2, and you had to solve for the volume. So they have like example 2 in the book. They'll ask you to do problems like that. They're always going to give you enough information that there's only one thing left for you to find. Now, another thing that they will ask you to do is either graph it or build a table of values and then graph it. I'll show you how to do both. And yeah, you can think of it like building a t-chart. And you get to pick the x's, and then you plug those numbers into the equation, you get the y's. But I'll show you a better way of doing that. If you can get it into y equals k over x form, then we can just put this into our y equals in the calculator, and then either make a table or graph it, or both. And so I'm going to show you that on the calculator here in like 12 seconds or less. Okay, I got my graphing calculator on again, and I put in the relationship 2 over x, y equals 2 over x. So you have a little button here that says table. It's right above the graph, so if you push your blue second button and then the graph button, you'll get this. And you can see there, you've got all your values, 1, 2, 3, 4, and all the y values, 2, 1, that's 2/3 and 1/2. So that's a table, and then you can just press graph and you'll see the picture. And if you want to double check on anything, you can hit trace and you can see all those values being mapped out along the graph. Last thing is you can actually change your mode to see both of those things at the same time. If you go down here to graph table, turn that on, when you hit graph, it'll show you the graph and it will show you the value of the table of values that corresponds to the graph. That should be enough to draw all the pictures that you need to for your problem set. If you have questions, leave them in the comment section below, or send me an email and I'll respond to you as soon as I can.